Okay, hello everyone. I'm Hiroshi Mukawa at the Sony R&D Center. And I have my colleague Christophe here, and we two are going to talk about AR/MR display in Sony to inspire kando. That means emotion in Japanese. Okay, and firstly, let me touch upon a bit about the metaverse, as this is a hot topic these days. The term metaverse firstly appeared in the science fiction book Snow Crash, written by Neil Stephenson in 1992. In the book, humans interact with each other and the software agents as an avatar in a 3D virtual space. But the metaverse, in the broader sense, that doesn't only refer to virtual worlds, but also includes the entire spectrum of augmented reality. Okay. So technologies such as extended reality, XR, computer vision, artificial intelligence, edge and cloud computing, and future mobile networks. All of these are the enablers that drives the transition from the current internet to the metaverse. Okay, then what's XR? As you know, XR, extended reality, consists of AR, VR, and MR. I positioned each of those three concepts based on whether they place more importance on virtual or real, and also whether they are to present a sense of reality or a sense of immersion or digital information. So today we are going to talk about AR/MR, especially optical see-through AR/MR near eye displays. Okay. And before diving into the display, let's look at the whole XR workflow. The display is a very important part, but it's just one of those elements. And as you can see here, it starts from the data capturing, then content creation, distribution, sensing and recognition, and end with the rendering and reproduction. And we need several technologies in each workflow. Here I picked up some important technologies. And for capturing, there are video, motion, and audio capture technologies. And for content creation, we need technologies for edit, codec, and computer graphics. For distribution, we use the internet or 5G at this moment. And for sensing and recognition, there are many technologies, but spatial sensing like SLAM, motion sensing, eye sensing, and object recognition, including semantic segmentation, are important. And computer vision plays an important role here. And finally, for rendering and reproduction, visual display, including rendering, would be one of the most important technologies, but audio and haptics are also crucial for immersive XR experience. Okay, here let me introduce the history of our near-eye display. We introduced the world's first head-mount display for consumers in 1996. And the first 3D capable micro OLED-based head-mount display in 2011. We call those products as a video viewing head-mount displays, as their main use case was to enjoy movies and videos. And also, we firstly demonstrated a full-color optical see-through AR glasses using our unique holographic waveguide technology at CE Show 2009. And using the same technology, the waveguide technology, two AR glasses like this, and also a display module were commercialized so far. And the Precision VR launched in 2016 And we introduced the MR head-mount display prototype in 2018. Okay, and this is our MR head-mount display prototype. It is a standalone and has stereo camera, IMU optical see-through display with dimming device in front side, and SoC and the battery in the back side for a better weight balance. And there are 5 features as described on the lower right here. And firstly, automatic see-through transmittance control by dimming device. And the second, hear-through capability with sound localization technology. Third, hand recognition. And fourth, real-time MR content sharing. And last, ergonomic design with one-to-one front rear weight balance. Okay. And we developed the custom SoC for this particular prototype to minimize motion to photon latency. And it consists of ARM-based CPU, a vision processing unit, which runs a proprietary real-time OS, and the GPU and the display controller. Then the special tracking and time warp functions are implemented in vision processing unit here to reduce latency and time jitter as well. And for the purpose of field test of the MR head-mount display prototype, we developed entertainment content using Ghostbusters IP, thanks to Ghostbusters Corporation. And this is a kind of indoor and outdoor MR game, shooting, collecting ghosts by a team of 3 to 4 people. And the first test was done at the Sony Pictures Entertainment in Los Angeles, and the second test was done at the Ginza Sony Park in Tokyo in 2019. And here I have 2 video clips showing some part of the content. And the first video is an indoor scenario like this. And so you will see the ghost is precisely registered in the glass box. And the blue female ghost called Katrina and the fire around the glass box are virtual images. And of course, the video was captured through an actual prototype. So please take a look. We had a sound. So those this the blue ghost and the fire around the glass box is the virtual image. And as you can see, those are the precisely registered to the physical this red box.
You can't stop anything as I assume the power of my ancestor, Vigo von Homburg Deutscheldorf. Oh, wow.
Okay, and so the second one is an outdoor scenario. You will see that players are enjoying the video game by sharing MR content with their friends. So let's see. Okay, and the video was captured in Sony Pictures loft, and it was sunny and very bright outside. But we still could see the virtual object clearly thanks to the dimming device. As you can see that those virtual contents were shared among those players. Okay, so so here is the feedback from participants, and we got lots of positive feedbacks, and there are these are the top 4. The first one is the sense of presence of a ghost by the video expression. And second one is again the sense of presence by 3D audio. And third, collaboration play with friend. And the final one is high image quality, both outdoors and indoors. And there are those technologies. Those technologies are enablers for those experiences. And of course, we also got some demands for improvement. And most common one was a wider field of view, especially along a vertical direction. So this is because vertical objects like this were sometimes truncated by the field of view, as shown here. You cannot see the very top of this the ghost. Okay, and the next we are going to talk about the challenges and some approaches of AR/MR near-eye displays. And here I would like to pass the baton to Christophe. So Christophe, please go ahead.
Thank you, Mukawa-san. Thank you very much. Do you hear me?
Yes.
Right. Okay. So yeah, I will not have version video like Mukawa-san. So yeah, so when we speak about field of view, as Mukawa-san showed before, there is this request. Basically, you want higher and larger field of view to display more people. So the reason is obvious, right? Field of view is as is display here. More you have field of view, for example, more you can see someone. So at 40 degrees, you can see someone around 1.70 m at 2 meters. However, next slide. Yeah. However, I think one of the key message we want to say here is the field of view is not one single number. In the human perception point of view, you don't see the same thing at the same field of view. So on this graphic here, you can see that, the field of view where you have very high resolution is very limited in a couple of degrees. Then you go where you can see shape, then you can see up to color. And then when you're far on the side, you don't have resolution, but you feel that there is a motion. So I think the first message that we want to say here is field of view is not a simple number. It's more complicated. So the next things, next slide, please, is when we want to build an AR or MR system, there's a big impact from comfort and sociability. So on this picture, this is what you want. Okay, that's what you have today if you have a pair of glasses. So this plays a big role of social interaction. You have eye contact. It's a fashionable piece. It's also comfortable. It's convenient. And it's also fitting with your visual health. You can wear it from the morning until the evening. But if you look at where is the form factor today, you can see that it's not at what you want or what you have today. So there is this disconnection here, just in terms of form factor, how you bring the technology in the form factor. And if you click next, yeah, also a very important system, which actually is a previous speaker speak about, is VST, version secondation conflict. You have to build a system that you are not going to feel discomfort for hours when you use it. So when you take the technology and all the consideration, you have to find what will be the acceptable form factor. So I think this is also another message we want to say. Where is the acceptable form factor? So to do mixed reality, you have two options, maybe three, let's say, if we speak about previous speaker as well. But here we speak about design. So you have the video see-through, where basically you capture the real world, you blend it with video and graphics with the virtual world, you blend the real and virtual world together, and you display this. This is video see-through. The other approach is optical see-through, where you let the real world go through, and you're going to superimpose on it the virtual world. So if you click here, so here it's a brief comparison of video see-through versus optical see-through. So of course, the image quality for video see-through is better compared to optical see-through. On the other hand, the real world image quality is better for the optical see-through. You don't need to reconstruct the world. Latency tolerance, video see-through, you have higher tolerance compared to the optical see-through. Now, if we speak about sociability, video see-through, you have outdoor use. It's very limited compared to the optical see-through. And also you don't have the eye contact, even if there's some development of some potential. So the second message is there is no perfect approach as well, video see-through versus optical see-through. If we go to the next slide, here we will focus on optical see-through, where we give a couple of elements here. Next slide, please. So optical see-through today, there is 4 main approaches to do it. So one is using freeform mirror. So basically you have a mirror, a system mirror. So you project your light on this mirror, which send back to your eye. So this gives you large field of view, large eye box, but form factor become big, but you keep optical efficiency. Then you have the bird bath approach, which is getting popular. So the lights go through a mirror, come back to enough mirror, go to your eye. So field of view is smaller than the form factor, the freeform, but also lower eye box. But form factor is a little bit better, and you still have a good optical efficiency. And then you have 2 more technologies, the retinal scan. I will come a little bit after to explain what is it, where in this case, the main limitation factor is the eye box, and you have the last column, which is the waveguide, which can use different optical engine, where you have relatively good field of view, higher eye box, good form factor, but now you suffer on optical efficiency. And see-through transparency is good. So here we're going to give you 2 examples of the retinal scan reflector and the waveguide. And the message here is when you pick up your technology, you have to think system level, all the aspects together. So that's what's important. So next slide, please. So retinal scan. So what is interesting in retinal scan? The concept is present here. So basically, you're going to scan all the pixels defining your image. So the pixels are generated by a laser, then they are scanned with a MEMS, sent to an hologram lens here, sent back to your eye. So what is great, and if you click, please, on this slide. So what is great with this technology is that it's a focus-free system. So you don't suffer of this divergence recommendation. The image, the focus of the image is fixed by the size of the image that you create. So if we go to the next slide, I think because we're running out of time, this video is going to explain. So if we can start this video. So this was demonstrated in 2019 in SIGGRAPH. So you see the image is displayed close to you here, and the hand is coming to show the focus. So here the image is at 25 centimeters. Field of view here is 47 degrees. And in terms of brightness, you have 10,000 nits. And this is where the same image now is focused in infinity. So you can see that you can really choose from very, very close to very large. By the way, unfortunately, we don't have time, but if you turn on the right, you can see more Fuji. And the last part is the waveguide combiner. So that's another approach. So here, the concept is you have an optical engine which creates your virtual image. This is projected by an input coupling inside the waveguide, light travel inside the waveguide, and you have a third grating, output gratings, which send back the light to your eye inside an eye box. So this eye box is a very important concept because inside this eye box, that's where you can move your eye and always see the image. So if we click here, so basically, if you want to use this technology, there's two main challenges. One is you need to make this waveguide small, efficient, and cost-effective. And basically, you have the same challenge for the optical engine. And next slide here. This is a free option, three main options that you can use for the waveguide. You can use holographic element, diffractive element, or cascaded mirror. And again here, you will see that there is always a trade-off here. For example, the diffractive ratings, field of view larger than the other, but efficiency lower. Holographic, low field of view, but larger efficiency. And good optical see-through. And if you take the cascaded mirror, for example, very good efficiency, but poor or low see-through transparency and manufacturing. So if we go to the next slide, this is an example of plastic holographic waveguide presented by Sony 3 years ago. And if we click here, yeah, so if we click on the video quickly, we will not go through to it because we have, but basically here it shows you, unfortunately on this image, you don't see the full color, but it's basically showing you around the 20-degree field of view made in a plastic waveguide with holographic film. So if we go to the next slide, so that's our message. Message is if you want to build an AR, MR display today, you have to run through a lot of trade-off, comfort, computer power, display specification. In display, we only speak about today a little bit field of view, but you have many more parameters. For example, light artifact, rainbow, etc. Product cost, sensing. And if we click, I think a message that we want to say and why we are happy to be joining this workshop is the display hardware alone cannot solve all this challenge. And the computer vision here can really be a big help to make this trade-off and take in consideration when you want to develop a device. And the last thing, because we're in a computer vision here, so Sony has running a research award program. You can go on this web page, etc. And the deadline for this year is passed, but it will open summertime 2022. And you can see that there is a lot of topic inside this website, which I think some of people on this code could be interested. So long story short, it's time to innovate at the hardware for display, but also in the computer vision. Thank you.